Hello, PCS 125. In this lecture that I'm posting, I want to do some extra practice with electric potential because it's one of the most tricky concepts that you encounter in this course. So we're going to do some practice, help you get you a little bit more comfortable with the concept of electric potential. And then I'm also going to do a little bit of exploring the relationship between electric potential and electric field. You know those two things must be related, but how exactly? That's what we want to get to here. So just to remind you some of the important concepts from what we've covered previously, these are the fundamental relationships. So this one and this one, we're talking about the relationship between electric potential and electric potential energy. So electric potential is potential energy per charge, okay? So it's sort of telling you about if I were to put a charge at a certain place, how much potential energy would it have? And that's what delta U equals Q delta V is telling you. So delta U is potential energy, change in potential energy. This is change in potential energy. Potential energy. And delta V is the potential difference or the voltage difference between the 2 points. So this is voltage difference. Potential difference, or the change in electric potential. So it's you have to keep those two things straight. They're related by a factor of Q here. And I keep going back to this analogy. When you're dealing with gravity, the closest analogy to electric potential is to height. So for example, this point here is, a certain distance above the ground. So I would say like the gravitational potential of that point is, 1 meter above the ground. It doesn't mean there's anything at that point. It's just like that point is telling me something about if I were to put a mass at that point, I could tell you how much potential energy that mass would have. Okay. The relationship between electric potential and electric field is given by this equation. This is the general definition, E dotted with ds, and along some path that connects state 1 and state 2. That's a bit abstract, so we worked it out in some special cases. So in the last 3 boxes on this slide are talking about special cases. In a uniform electric field, so the electric field is constant magnitude, constant direction, this integral is easy to do because then E is constant. It can come outside of the integral. And I get that the potential difference between 2 points goes linearly with the distance or with the displacement. Specifically, it goes as the dot product, E dotted with delta S, where delta S is a vector connecting the 2 points, 1 and 2. So that's a uniform E field. What if you have a single point charge? What's the electric potential from a single point charge? That's on the right here. So V of R is KQ over R. It looks a lot like the force, KQQ over R squared, or the electric field, KQ over R squared, but just be careful. This one has only one R in the denominator. It's not a vector, it's just a number. Electric potential is a scalar. And then what if you have 2 point charges? They have an electric potential energy, which is the third equation on the bottom there. KQ1 Q2 over R looks a lot like the potential between gravitational potential energy between 2 masses, Gm1 M2 over R with a minus sign. Okay, so those are some special cases. This is a kind of review of what we've done so far. So what I want to do here is just basically hope that you have an increased understanding of electric potential. I'm going to go through it a little bit more. Hopefully it gets it a little bit clearer, and hopefully you're getting some practice visualizing electric potential in terms of like height. So think about hills and valleys. Positive charges create hills, negative charges create valleys. And then this is going to be the new part here. Be familiar with how to get an electric field from an electric potential and vice versa. Okay, so again, this is just the kind of visualize the electric potential. If you have 2 point charges, plus and minus, for example, we know we have some electric field lines that are connecting those two. So the red lines are the electric field lines, and then the dashed green lines are the equipotential lines. So I like to visualize this as kind of like a landscape, right? The positive charge is a big mountain, and these circles are lines of constant height, right? So the closer I get to the positive charge, the more uphill I'm going, the higher potential. And the closer I get to the negative charge, the more downhill I'm going into like a well here, okay? So this was what it looks like for point charges. The positive charges create hills, the negative charges create valleys. If I were to put another point charge somewhere like here, let's say, plus Q, the positive charge would roll down the hill towards the negative charge. So positive charges roll down the hill towards the negative charge. That makes sense because positive is attracted to negative. And same thing if I put a charge here like plus Q, it would roll down the hill away from the positive charge. But if I put a negative charge somewhere, maybe I'll use a different color, like put a negative charge here, plus, minus Q, that would roll uphill. Okay, so negative charges are weird. They kind of roll uphill, not the way that normal masses behave. Normal masses behave like positive charges. Masses roll downhill, positive charges roll downhill. Negative charges are the weird ones. They roll uphill. Now, what I wanted to do is to give you a little extra practice with constant electric field or uniform electric field. So imagine you've got two plates, really, really big plates. We talked about the fact that the electric field is constant inside those. Now, remembering this formula here, delta V is equal to minus E dotted with delta S from A to B. You can see that in a uniform electric field, the voltage difference will change linearly. And that's kind of what I'm illustrating on this slide here. So let's suppose I've got a negative plate here. Let's call that 0 volts. And then maybe I hook this other plate up to a battery, which is 30 volts. Okay, so I've got a 30 volt potential difference between the two plates. The question is, what is going on in between? And according to this equation here, you can see that the voltage change is proportional to the distance, right? It goes linearly in the distance. And so if I go 1/3 of the way from the negative plate up, like here on this line, the voltage will be 10 volts. And if I go 2/3 of the way, it'll be 20 volts. So it behaves linearly in between plates like that. Right halfway between, what is the voltage? The voltage would be 15 volts right halfway between. So the voltage change is proportional to the distance when I am in a uniform electric field. And that's the situation you have when you have two charged plates. Okay. There's a lot of problems that show up when you have charged plates, and these kinds of problems show up a lot in solid state physics, especially when you're considering like the photoelectric effect, which is something that will come in future classes. So here's an example of that kind of problem. A dust particle with a certain charge, you know what it is. It has 0.2 joules of kinetic energy at the position shown. It's between two large plates with an applied potential difference of 20 volts. Okay, so I've hooked this thing up to a battery. The right side has a potential of 20 volts and the left side has a potential of 0 volts. So there's a potential difference of 20 volts between those two plates. When this charge has traveled 2 centimeters, what is its kinetic energy? And by the way, you notice that the distance between the plates is 10 centimeters. Go ahead and pause the video, see if you can think about this one, try to work it out before we go forward with it. So hopefully you have chosen one of these answers now, committed to one of these, and let's talk about it exactly. So the conservation of energy problem, I want to know when it's traveled 2 centimeters, I want to know what was its change in potential energy. If I know that, I can determine its change in kinetic energy because I know the conservation of energy, delta K plus delta U is equal to 0. Okay, so my question is, what is this? Well, I know it's Q delta V because the change in potential energy is related to the potential difference by this formula Q delta V. Now, what is delta V? If I went all the way across from 0 from one side to the other, delta V would be 20. Okay, but I'm not traveling the whole 10 centimeters. I'm only traveling 2 centimeters, right? So I'm traveling 1/5 of the distance. Remembering that between two plates, the voltage change is linear. If I go 1/5 of the distance across the plates, I will go through 1/5 of the voltage change. Okay? So what's 1/5 of 20? That's 4 volts. So when I go through 2 centimeters, I've gone 1/5 of the distance. I've traveled through 1/5 of the total potential difference between one plate and the other. And so I will have gone through 4 volts. Okay, so that's the key observation here. This will be 4 volts because it's the only 1/5 of the way across. Once I know that, I can just use my conservation of energy equation. Delta K plus delta U equals to 0. So delta K is minus delta U. Delta K is KE final minus KE initial is equal to minus delta U. And delta U is Q delta V. So, okay so far. So then my final kinetic energy is my initial kinetic energy minus Q delta V. Then I plug in the numbers. What is my initial kinetic energy? That's given, 0.2 joules, 0.02 joules. Q is given, 0.0025 coulombs, times 4 volts. Remember, the 4 volts was because I went 1/5 of the distance across. And when you plug those numbers in, you get 0.01 joules. So there's a kind of classic problem involving a particle moving some distance in a uniform electric field. You can figure out its kinetic energy by knowing the distance that it went and the voltage difference that it traveled through. A couple more notes about electric potential. I mentioned this before, but there's an electric potential at every point in space, even if there's no charge there, just like electric field, right? And also gravitational field, like this point, there's nothing here, but there's a gravitational field there, and there's a height. I can say that this point has a certain height above the ground. It's the same way with electric potential. I would say this point has a certain voltage, even though there's nothing there, and it might also have an electric field at that point. When we're talking about voltage or potential difference, it's always best to talk about the difference between 2 points. It's the difference in voltage between 2 points. That's really what controls physics, is the difference between 2 points. For those of you who are electric engineers, if you have a voltmeter, it's designed to measure potential difference between 2 things. And it has 2 leads, which you connect to different circuit elements, and it says, what's the difference in the voltage between those 2 points? So you always talk about differences in potential, because you're interested, that's what really shows up in problems, because the change in potential is related to the change in kinetic energy. Right? So we're always interested in the change in voltage between 2 points, or the difference in voltage between 2 points. It's a little confusing because we've given this formula, KQ over R, for the potential distance at a distance R away from a point charge. And you have to say, well, that's the difference between which 2 points? It turns out that that's the difference between that point and infinity. So remember, I set 0 to be at infinity. And so when you're thinking, like, what is the other point here? It's really the one at infinity. So V equals KQ over R is really the difference between the point that I'm looking at and the 0, which I set to be infinitely far away. Here's another question dealing with point charges. Suppose I've got 4 point charges arranged in a square like this. They're all positive, and they're all going to be identical point charges. Which of the following is true at the center? So I want to know at the very center of this square. Think about the electric field and think about the voltage or the potential. Are they both 0? Is only one of them 0, or neither of them 0? Take a moment, pause the video, see if you can answer this question before proceeding. Hopefully you've committed to one of these answers now. Okay, so think about it separately, E and V. Maybe I can consider this 1. Let's label them 1, 2, 3, and 4, all the charges. What's the electric field at the center from charge 1? It points away from charge 1. So this I would call E1, let's say. And what's the electric field from charge 3? Well, that would point away from charge 3, so that would be like this, right? This would be E3. And hopefully it's not too hard to see that those two, E1 and E3, have exactly the same magnitude but opposite directions, because the charges are identical and the same distance from each one, and so those two will cancel. And in the same way, I would have 2 fields like this from the other 2 charges. So this one would be E4, the electric field from charge 4, and this one would be electric field from charge 2, and those would all cancel. So I've got to have electric field equals to 0. I'm stuck with either A or B, because all of those electric fields are going to cancel out at the exact center of that sphere, or of that square. Now, how about the potential? Is it 0 or is it not 0? If you think about the potential, remember that V of R is KQ over R. And R is the same for each of these. R is the distance from the point to the charge. So I would say V1 is KQ over R1. R1 is this distance here, right? And then I would have the same thing. V2 is KQ over R2. And it's the same distance. So that's this distance here, and so on. V3 and V4, those are both KQ over R3 and KQ over R4. All of those things are positive, right? The R that goes into there is a distance, so that's positive. The charges are all positive, so there's no way I could have zero potential at the center of the square. They're all going to be positive numbers, which I add up. So the correct answer on this one is B. The electric field is 0. The electric potential is not 0. Okay. And you can visualize that using this charges and fields applet. So there's a link to this on D2L. I put up the 4 charges, and these yellow dots are sensing the electric field. So you can see there's an electric field this way here, and this way here, and this way here. I put one right at the center. You can see the arrow is not there. The arrow is, so there's no electric field. But you can measure the electric potential. That's what these green lines are. These are constant equipotential lines. If I put a voltmeter at the center, it reads something not 0. In fact, I didn't want to get right on top of this yellow one, but it's reading 25.54 volts near the center. And this makes sense because this is a mountain, this is a mountain, this is a mountain, this is a mountain, right? So I've got 4 mountains, and then I'm kind of in the middle of those 4 mountains. It makes sense that I'm not going to be at sea level because I've got mountains all around me. Okay. Here's another example we can work on using electric potential and conservation of energy. This one involves point charges. So a dust particle of mass 3 milligrams, negative charge, is brought to point A and released. What will be its speed when it reaches point B? You've got these 2 other positive charges, 1 microcoulomb each. Those are held in place and cannot move. Pause the video, see if you can work this one out yourself before going forward. Okay, so let's try to work this one out here. Here's our strategy. I want to find the potential difference between A and B. So I'm going to find delta V, which is going to be the potential at B minus the potential at A. Once I know that, I can find the change in potential energy, delta U, is equal to Q times delta V. And then I'm going to use conservation of energy. So let's try and put that plan into action here. What's the electric potential at A, VA? So let's call this one charge 1, and this one will be charge 2. It's KE Q1 over R1 plus KE Q2 over R2. But in this case, R1 and R2 are the same. So R1 is this way, right, from A to the charge, and R2 is this distance here. Those distances are the same. So I'm going to have here 2 KEQ over R. Let's say R1. Doesn't matter, could be R1 or R2. Let me introduce a constant here. Let me call this constant here A. Okay, so A is going to be the distance from the charge to the center point. And that A is going to be 1 centimeter, I think, right? Sorry, it's going to be 2 centimeters because 4 centimeters between the charges. But this height is also 2 centimeters. So this is also equal to A. And that means R1 and R2 are the square root of 2 times A by the Pythagorean theorem. So I'm going to have 2 KEQ over the square root of 2 times A, just like that. Okay. Now what about at point B? What's the potential at point B? Same idea. I'm going to have KQ over R, but now R is just the distance between point B and the charge. So it'll be like KEQ over A, because I'm looking at the potential here, plus another KEQ over A, because the distances are the same, the charges are the same. So this will be 2 KEQ over A. What's the potential difference? That's VB minus VA. So that's 2 KEQ over A minus 2 KEQ over square root of 2 times A. And this you can simplify. There's a 2, there's a KE, and there's a Q, and there's an A in every term. 1 minus 1 over square root of 2. This is delta V. That's the potential difference between those 2 points. So we did that part. Now find delta U is Q delta V. That's easy enough. Let's go to the next slide. So now I'm going to use conservation of energy. Delta K plus delta U is equal to 0. Dealing with electric potential energy, I always use Q delta V. My potential energy is Q times the potential difference between the 2 points. Okay, this is K final minus K initial. K initial is 0. Plus Q. So this is the charge of the dust particle, which is moving between those 2 points. Times delta V is equal to 0. I've got K final is equal to minus the charge of the dust times delta V, which I'm going to substitute the formula from the previous slide, which was 2 KEQ divided by A, 1 minus 1 over root 2. So this was from the previous slide. I'm trying to find the speed. What will be its speed? So I got to use 1/2 mvf squared is equal to that whole thing on the right side. And solve for VF. So VF will be equal to, I got to multiply by 2 to get rid of the 1/2, and I got to divide by the m. So I'm going to have here minus 2 multiplied by another 2 is 4. KE Q dust divided by m times A. I divided by the m from the left-hand side. 1 minus 1 over root 2. And then I have to take the square root of that. So I did a few steps at once. Solved for VF by multiplying by 2, dividing by m, taking the square root. Now when you look at this, you're worried. You're like, wait a second. Isn't this going to end up being the square root of a negative number? But in fact, the numbers are going to work out. So let's plug in the numbers now. We take that same formula, VF, we write it up here. Okay, 1 over root 2 is less than 1, so that's fine. And you're worried about this minus sign here, but this is a negative number, so the minus signs are going to all cancel out. So what do we have? If I plug in the numbers here, I'm going to have minus 4, Coulomb's constant, 9 times 10 to the 9, Newton meters squared per Coulomb squared. The charge Q is 1 microcoulomb, so that's 1 times 10 to the minus 6 coulombs. The charge of the Q dust is minus 2 times 10 to the minus 6 coulombs. So you can see that minus is going to cancel the other minus. Then I've got 1 minus 1 over root 2 here. Divide by m, 3 milligrams. That's 3 times 10 to the minus 6 kilograms. Times A, which is 2 centimeters, so 0.02 meters. Check the units. Coulomb squared. On the bottom, there's a coulomb and a coulomb. All the coulombs cancel out. I've got a meter on the bottom, which is going to cancel with one of those meters on the top. Newton meter over kilogram. What are the units here? The units of VF. I've got square root of Newton times a meter over a kilogram. Remember that a Newton is a kilogram meter per second squared divided by a kilogram times another meter. And I've got square root of meters squared per second squared, so this is meters per second. So the units make sense. Plug in the numbers, I get 593 meters per second. So there's an example involving conservation of energy, dealing with the electric potential from point charges. Last thing I want to cover is what's the relationship between electric field and electric potential. Going back to my gravitational analogy, electric field is like the slope of the hill. It's the thing that's going to accelerate the charges, right? So that if I put a mass, going back to the hill analogy, if I put a mass here, it's going to start rolling kind of slowly. But if I put a mass here, it's going to roll a lot faster. The steeper the slope, the larger the gravitational force, and the quicker the object will accelerate away. It's the same idea when it comes to electric fields, that the slope, or where those lines are closer together, it means there's a steeper slope, and so I'll have a stronger electric field. The electric field always points from high potential to low potential. It points down the hill. Okay, so again, this is the kind of top of the hill here. And then the electric field is pointing down the hill from high potential to low potential. And you can see like where the lines are more closely spaced, I've got a steeper slope, and where the lines are more further apart, I have a more gradual slope. So the electric field is stronger over here and weaker over here. And right over like this part here is where it's the strongest. Mathematically, how do you calculate it? Got to go back to this formula here. Delta V is equal to some kind of integral. So what if I know V and I want to know E? V is related to E by an integral. You need to undo the integral. So the opposite of the integral is like a derivative, right? So the E is going to be the derivative of V in some sense. And there's only one problem, is that electric field is a vector, but potential is not a vector. So you need a special kind of derivative. It's called a gradient. This will be something that you will get to in your later calculus classes. But the idea is basically, if you want to know the x component of the electric field, you take the x derivative of V. If you want to know the y component, you calculate the y derivative of V. And if you want to know like the r component of the electric field, if you're looking at the radial component, let's take the dV/dr. So basically, E is a derivative of the electric potential with a minus sign in front. Let me put that to the test with this clicker question. Suppose you've got an electric potential which looks like this. So this is V as a function of x. It has this shape here. I want to know, where is the electric field bigger? Is it bigger at XA, bigger at XB, or both the same? And sorry if this is not on the screen. So this is supposed to be XA here, and this is XB here. Where is the electric field bigger? Pause the video, see if you can answer this before going forward. Okay, so hopefully you've chosen one of these answers now. The answer is that it would be bigger at A. Again, this is XA, and this is XB. Be bigger at A because the slope is bigger there, right? Derivative is slope. So the bigger the slope, the bigger the electric field. So I've got a steep slope here, and I've got a kind of gradual slope here. So the bigger the slope, the bigger the electric field. So A has a bigger slope. Let me try to summarize. Electric potential is potential energy per charge. It's kind of like height when you're dealing with gravity. That's the closest analogy. Positive charges create hills, negative charges create valleys. So you can think about like a positive charge is creating a mountain in this space, negative charge is creating a valley. If you put another positive charge on the hill, it rolls down the hill, but negative charges are weird, they roll up the hill. If you need to know the electric field and you know the potential, you can get the answer by taking a derivative. So in particular, these components, dV/dx is the electric field in the x direction, minus dV/dy is the electric field in the y direction, and so on. So I hope you have a little bit better understanding of electric potential here and with those examples, and we will pick it up here and talk a little bit more about conductors in the next lecture. Thanks again for all of your attention. Bye for now.